Live, so no more. Well, welcome everyone. My name is Rob Spiak. I'm Research Manager for the Applied Research and Commercialization Department here at Red River College. Great to see such a good turnout. Welcome all of you to this Lunch and Learn session entitled Winnipeg International Airport, Sustainable Design, Enhanced Performance. First, I want to give a couple acknowledgements for the event. It's been made possible through our NSERT grant entitled Improving the Energy Performance of Buildings. So I'll talk a little bit more about that. Cassidy and Terry from our Technology Learning Center, and also Brent and Adam, who work and do all our communications, write up all kinds of good stuff for us to put on our blog and get the word out of what we're doing. So with our NSERT grant, it's a 5-year, $2.3 million grant that commenced in 2009. It's intended to build the college's capacity in the increasingly important area of energy efficiency in buildings. And the grant's intended to build our capacity, and so to bring staff and students and faculty together to do applied research projects. To date, we've had a number of different projects, some of which a lot of people are familiar with. The big solar trough outside is one, and yes, it's running again. We've debugged it to the nth degree, so it's making heat now. We've done numerous student projects with lighting, novel materials for lessening embodied energy in buildings, infrared thermography, the list goes on. We have 7 student interns in our office this summer. They're all here right now. You guys all wave. They're all back. We made them come. So right now, the big thing that we're doing with 4 of them anyway is an air leakage investigation of large buildings. So there's a big knowledge gap. We've got a lot of data on small buildings, residential. Large buildings, we don't really know the air leakage characteristics of large buildings. It's only been a handful of tests done. So with the support of Manitoba Hydro and our NSERT grant, we're going to do a study of 20 buildings and hopefully more. I think we'll get more done and find out how leaky buildings are and more importantly where they leak too. So what else have we been doing? Thermal performance testing the wall sections. We're developing that expertise right now. We have our electronic students are doing a great job working on that with heat flux sensors. We've done testing of a vertical axis wind turbine, and I wasn't here to see it, but it didn't blow up and hit anything. I heard the test was really, really well executed. And we've got a number of other projects that are being developed. And also, looking to the future here, I wanted to introduce our new Green Buildings and Construction Research Chair. It's Chakri Rashan. He's sitting at the back. So he's going to be working to build on the momentum we've started to gain with the NSERT grant right now, and we're looking to transition into a services and training center called the Technology Access Center. So we're approaching NSERT to get some continued funds to transition into that, because our NSERT grant isn't renewable. So today, getting on with the presentation, we welcome Russell Lavette. Hope I'm pronouncing that correctly. He's Senior Mechanical Engineer with SMS Engineering Limited. Russell has over 20 years of high-vac and controlled system design experience, very well versed in the design and construction of facilities that are both large and small. His involvement in projects such as the Winnipeg James Armstrong Richardson International Airport redevelopment, University of Winnipeg Richardson College for the Environment, and also the Investors Group field, the Winnipeg Stadium, which is going to get tested tonight, I guess, speak to the depth and breadth of his knowledge and hands-on experience that he has. Russell has held the volunteer position of Society Chairperson for Membership Promotion for ASHRAE. That's the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And he was responsible for the direction of an international committee responsible for the maintenance and growth of the Society's membership. And also, a little more about Russell. He's a LEED accredited professional since 2006, and he's been involved in many projects that are currently undergoing final review by the Canadian Green Building Council for certification. And Russell's a registered professional engineer in Manitoba and Ontario, and he resides in Winnipeg, so he knows about cold and mosquitoes like the rest of us, and he's well experienced in travel throughout the US and Canada. Russell's talk will be about 30 to 35 minutes, so there'll be plenty of time for questions and answers afterwards. So with that, I welcome Russell.
Okay, thank you. So for the students out there, thank you for coming. I know you're forced to come. It's great when the speaker has to have an audience. It works so nicely. So good afternoon, everyone. I'm going to speak today about this building. It's been called iconic, unique, and it's definitely been celebrated across Canada as an architectural wonder. It's been a privilege to work on this project. I worked on this, it's now been over 8 years, since the very first start of the project back in 2004. The formal name of the building is the Winnipeg James Armstrong Richardson International Airport. And we're going to discuss specifically the air terminal building, which is this building, and the related power plant, the central utilities building, which generates all of the energy and achieves some of the energy performance for the facility. I'm going to talk specifically about the main question, which is whether the sustainable design approach that was used on this project, whether it enhanced the performance of the building and how it did so. I'd like to start, though, with a bit of a history of the project itself. You all remember the old airport, which is now gone, apart from the administration building, which still remains. The Winnipeg International Airport was originally oh, sorry. Wait. It's back here. No problem. Is it good? Okay. The Winnipeg International Airport was originally a Transport Canada facility. It was taken over in 1997 by the Winnipeg Airports Authority, and as part of their stewardship, they did a review of the airport infrastructure, and it determined that really it wasn't going to last very long. It was an older building in poor shape and would eventually require replacement. So they went through a number of analyses of the facility, and it was quickly determined that projected air traffic growth, coupled with the wear and tear on the existing facility, that the building would have to be replaced within the near future. And they started to investigate what they wanted in terms of building and determined they wanted a facility that would last well into the 21st century and offer the best possible airport for Manitoba's usage. So preliminary studies were undertaken to determine needs and a vision for the project, and the Airport Authority took their stewardship very seriously and saw a need to create a sustainable aspect of their portal, the portal into Winnipeg and into Manitoba. So a call for teams, and it included a requirement for the new airport facilities to include sustainable elements that would guide the project towards energy efficiency and awareness of sustainability as part of its mandate. And definitely awareness of the impact of the facility to the environment within the city of Winnipeg itself. This again is a shot of the inside of the old airport back in the 1970s. So as the project progressed, and the design team of Stantec Architecture, who we worked for, working with Pelly Clark Pelly Architects, Caesar Pelly is the leader of that firm. They're from New Haven, Connecticut. We began to incorporate the newly developed LEED program, which stands for Leadership in Energy and Environmental Design, as part of the project requirements. And this is at the very start of the LEED program being unveiled in 2001, 2002. So it was all a new experience for all of us involved to understand what the LEED process is all about, what becoming LEED accredited is all about, and learning to work with designs in a different manner where you're starting to look at sustainability as the basis of a lot of the design decisions, as opposed to just designing a building to heat or cool and to be comfortable. This is one of the original sketch plans that we had at the very start that showed the old air terminal building here, the administration building, the hotel, and the central utilities building. I want to show you this because it explains the relationship between the two buildings really well. If you've been to the campus, you know there's a parkade on the site, which was eventually located somewhat here. And the concept for the new terminal building was over here, basically where it sits today, to the north of the old terminal building. What we had to create, sure, not working? Okay. Sorry, what we had to create was a tunnel link from the existing central utility building across into the new terminal building. I'll speak a little bit about that. So what were the sustainable elements in the project? For those of you who aren't familiar with the LEED program, I'm just going to spend a few minutes talking about it so you can understand what the challenges are about it. The LEED program is based on points earned by achieving various elements of sustainable design outlined in the specification book that LEED has as to how you're supposed to design a building under that program. It's not the only program that exists in the world for designing green buildings, but it's one of the more popular and definitely one of the most recognized in North America for sure. The concept is that in LEED, the more points you earn by the things you do in the design, the better the project performs. And the greater the level of recognition is ascribed to it as a result. So if you earn more points, you get better classification of your building and so on and so on. There are 4 levels available, certified being the lowest level, silver, gold, and platinum. It's sort of you can think of it as Olympics of sustainability. It's sort of that similar concept of medals. So for a certain number of points, you get a certified building. For a greater number of points, you get a silver building, and so on, up to platinum being the highest possible rating under this system. The airport project aimed for silver as its goal, and we're going through the final process of having that accreditation verified. So there's a few bits and pieces of information that still have to go to the Canadian Green Buildings Council, but we're expecting the building to achieve silver at this point, as was intended at the start. And that's a significant achievement for a building of this size. It's over 600,000 square feet. It's 3 stories tall, it's almost completely wrapped in glass, and it's in the middle of a prairie in Manitoba. So in the winter, when the cold Arctic air comes down from basically the North Pole, there's no other large building north of this facility anywhere in Canada. So it's basically, you're getting the wind direct from the Arctic coming down the prairies and running into the facade of this building over here along the north face. So it gets the Arctic wind in the wintertime. In the summertime, there's a humongous solar load placed on the building by it facing directly south on this facade over here, and also the back of the hold rooms. And there's also just the fact that there's a lot of wind in Manitoba that causes pressure issues inside the building, that we had some issues trying to resolve all of that. Again, this facade is approximately 450 meters long. So it's a massive element in the middle of an empty prairie, basically. So it basically forms a wall to anything that's pushing up against it in terms of air or snow. What's interesting is this, in the summer versus the winter, Manitoba is very unique in that we have a very great differential temperature between winter and summertime. We can see winter lows as low as minus 4 degrees Celsius or minus 40 degrees Fahrenheit, and summer highs as high as 35 degrees Celsius or 95 degrees Fahrenheit. It's one of the most wildly fluctuating environments in North America, and as a result, this building poses a significant challenge to us because the concept the architects had was to have it completely transparent. When you go to the airport and you drive up and get out of your car at the front door, you can see through to where the planes are waiting for you on the other side of the security line. The concepts the architects wanted to maintain was the visualness through the building, the ability to see the prairie from the front door, because there is a field behind it that is the airport campus, and so nothing will ever be built on it. So that is the reason why the roof line is very low, and the feeling once you're inside there is a compression when you go through the doors, and then expansion of the ceiling space, which is 3 stories tall once you walk in, to give you that sense of openness and vastness of the prairie. And the wood tones and the ceiling all add to that as well, too. So our challenge as design engineers on this project was that when we embarked on this project, given the building systems engineering we had to do, we were presented with a really significant challenge in trying to make this building work efficiently, because intuitively, when you look at it as an engineer, you say, this isn't going to work. It's a gigantic fish bowl. It's all glass, and how do you heat and cool that thing effectively in the environment we work in here in Winnipeg? So the LEED program describes a large portion of available points to energy usage, a very, very large portion of that. So the main approach was to ensure the building uses whatever energy it consumes as efficiently as possible. You can't not use energy to heat or cool a building like this, but the idea is to make sure you use it wisely and use it effectively, and you reuse it if possible at all. And we did get into that as well, too. And just another view of the aerial photograph rendering. This is the north orientation, the south over here. And the central utilities building is back over here. So let's talk about the heating systems first. Initially, the new air terminal building was to have its own heating and cooling plant within the building. But as part of the whole LEED process, the sustainable design process, we started to look at options to perhaps reuse the then 45-year-old central utilities building, which is serving steam and chilled water to the existing airport at that time, and the administration building. There was some rationale saying, well, while that building's 45 years old and the equipment inside it is 45 years old, there had been a couple of replacements of chillers that had happened already, and there seemed to be some logic in saying, why would we spend a whole bunch of money on building structure, space within the airport when there's already an existing power plant over here? The only challenge was to get a tunnel from this power plant over to the air terminal building. So that tunnel was eventually put in. Our firm didn't do the engineering on it. It was another firm that, as part of the overall campus redevelopment program. But what they ended up with was a tunnel that runs along the parkade over here, under the roadway, and into the basement of the building, basically in this area over here. And you're seeing a shot down in the tunnel just prior to the opening of the facility. The biggest challenge with this tunnel is there's tons of existing services on the site. But again, the sustainability approach to the project made sense to try to put the tunnel in between all the services. So that's why you see the floor moving up and down here as it goes over top of a sewer and below something else. And when you walk down that tunnel, it's quite the exercise to go up and down various spots, but it does actually connect the two facilities, and you can walk through it from end to end. So basically, as I mentioned before, the heating and cooling plant are at the far end of the tunnel, and we're bringing chilled water, which are these two lines here, and heating water up on top from the central utilities building into the air terminal building, and doing it all from a remote powerhouse. Again, maintaining the scheme of the original airport. So the terminal building is heated using hot water generated at the central utilities plant, and we use a unique approach to make use of that hot water. So we're sending hot water at a relatively high temperature, 180 degrees Fahrenheit, which is 82 degrees Celsius, bring it into the building, and then using a cascade approach to use the energy as effectively as possible. So that hot water, you can't touch it, it's that hot. It's not boiling though, comes across through the tunnel into the terminal building, and we first send that very, very warm water through all the heating elements on the perimeter of the building. So anywhere you have a door, an entry door, a rolling door for vehicles to go inside or out, or any aspect where you might have a window where you have, say, a radiator at the base of the window, we're running the hottest temperature water to those elements first. They see the greatest temperature differential, so they cool off relatively quickly in terms of the water going through that device. So the water entering is at 180 degrees, the water leaving is at 150 degrees. We then take that medium temperature water and push it through the air handlers. So we then heat all the outside air with that medium temperature water. We drop that water temperature down from 150 degrees Fahrenheit down to 100 degrees Fahrenheit. And we'll talk about why we do that in a moment or two. So what we do is we take the very, very hot water, rather than sending it back to the boilers at the powerhouse at a low temperature, we get it down to a very, very low temperature. And that allows us to do a couple of interesting things. We then take the water in the powerhouse and run it through an additional energy efficiency device, which is this device here. This is some of the heat exchangers in the basement of the air terminal building that deal with the various temperatures of water, I should say, and one of the main pumping stations. So some fairly hefty equipment that does all this work. But in the central utilities plant, we use a very unique device that is called, if I can find it here, flue gas condensing economizer. What it does basically is we have two sets of boilers in the powerhouse generating energy for the campus. There's two steam boilers, two 400 horsepower steam boilers that generate steam for the remaining existing buildings, because the original campus is all on steam. So that maintains the administration building and a few other small buildings that need steam heat. We then have two brand new hot water boilers, both 400 horsepower as well too, that do the hot water heating for the air terminal building. When all that equipment's in operation, we take the flue gases off those boilers, so the exhaust basically off the chimneys, and we run it through this machine over here, which I should stop pushing the wrong button. What this does is it condenses the flue gas from the boilers and allows us to extract that additional energy from the flue gases. So what the net effect is for the overall power plant, we run at about 97 to 98% efficiency, where the old plant was around 65% or 60% efficient. So there's a drastic increase in the efficiency of the plant as a result of that. The reason why we want to get the water down to 100 degrees is because we want to condense the flue gases in this device. So we're taking that water and basically spraying it into so there's a spray of water going downwards in this device. The flue gases are going up to the chimney. Those two streams interact with each other, and what ends up happening is the water that's held inside the flue gas or the boiler exhaust is condensed, and that releases energy. We pick that energy up and put it back into the preheated water going back to the boilers. So what that allows us to do is to gain that additional 10 to 15% efficiency on the system and allow us to get a very, very highly efficient plant on a campus of this scale. So we'll just talk quickly about some of the electrical aspects. Again, my line of expertise is not electrical engineering, but I'll speak to it nonetheless. Generation of emergency power was the critical issue on this particular project because the airport has to remain operative at all time. When there's planes in the air, they have to be able to land somewhere. Winnipeg, you may not be aware of this, is an emergency landing point for many aircraft going overseas across the Arctic or east to west across North America. That's why you always see planes flying at high altitude over top of Winnipeg, because they're crossing a point where they could land if they have to. And so it's a critical airport in terms of emergency services for all airlines throughout the world. As a result of that, the airport itself cannot shut down. It can't handle a power failure because all the lighting goes off on the runways. The building can't be serviced. You can't bring passengers in and out of the building. So the airport authority mandated us to design a fairly robust electrical system. So there are in fact two main feeders coming from Manitoba Hydro onto the campus to the main electrical distribution in the central utilities plant. And we also have two megawatt generators on site. So the entire building can go into emergency power if there's a power failure from either hydro or a problem internally with cables or breakers having shut down. So that means all the lights stay on, everything in terms of cooking for the restaurants, services, the baggage handling equipment, the boarding bridges, anything that's powered electrically remains in operation if there's a power failure. We had a relatively dramatic test a couple Christmases ago, just after the building opened. One of the transformer switches actually failed on us on the main feeder. Just happened to fail. And so the building ran for about 4 or 5 days on emergency power nonstop. The only challenge there is just make sure you have enough diesel fuel on site. There's a 25,000-gallon tank on site, which can be filled up relatively quickly by a tanker truck when necessary. But we did run a test for 4 days inadvertently and demonstrated to the airport authority that the design was in fact robust. All the safeties did come into play, and we maintained power on site for that required time. Just in terms of the heating and cooling again, the chilled water for the facility is generated in the powerhouse as well too. We have 5 550-ton chillers there, so there's about 2,500 tons of capacity available. They don't actually use it all, but it is there available. And those are high efficiency machines as well too. Again, part of that scheme to design a highly efficient system. So a couple of design issues that came up in terms of sustainability that really surprised us. This is a photograph of the three-dimensional model they had created at the start of the project. This is not a digital model, this is a real-life cardboard and plastic model, so that we could look at various things and also to demonstrate to the public what the building would look like once it's finished. What you're looking at here is the hold room, the end of the hold room. If you've been in the buildings at the very far end, if you walk right to when you come up through security to your left, right at the very far end, it's basically 3 or 4 stories of glazing. This area over here, and it's transparent right through. There's glazing on both sides of the building. When we were doing our calculations to work out the heating and cooling loads for this part of the building, we ran into something very odd. We use computer software to do this, obviously. And normally when you run through all the software, you get a positive output of the computer. The computer says you need to add this many BTUs or kilowatts of energy to heat the building. We had opposite numbers come out in the modeling. So we said, well, that's not right. We've got to do this by hand. So the guys went and cranked it out by hand. They got the same answer the computer got. So there wasn't an error in the computer software. It took us about 2 days to figure out what was happening was the solar gain from this, and this is in the winter time, the dead of winter, January, coldest night of the year kind of thing. The solar gain in this part of the building is so high that it can in fact heat itself just with the sun. And so an additional sustainable thing came into play now, that we could use the solar gain in the building to actually reduce the amount of heating we needed to make the building work because of the glazing element. And that was sort of a surprise. We didn't expect that to happen. We thought the opposite would happen, that there'd be so much glass that we'd be losing heat through the glass all the time that we'd have to throw all this extra heat in, but we actually got the benefit of the sun when it's out. So that was one interesting story. The other one is to do with the curtain wall itself. It's not a fancy curtain wall. It has some fancy etching on the glass to reduce the glare on it. That's sort of this light gray stuff, these lines you see over here. That's more just to reduce glare when you're inside the building. But a standard curtain wall typically you see to most commercial buildings in Manitoba. And we were presented with a further challenge by Cesar Pelli and his team that they didn't want to see any radiators at the base of the windows, as you typically see in Manitoba, in cold climates. They wanted the window to come right down to the floor and terminate there, so there'd be nothing in the way of you seeing what's outside the building. I don't know if you're lying on the floor looking outside the building, it doesn't make sense to me, but it's the architects were like that. So the challenge we had there was, how do you heat a space without having perimeter radiation when you have, say, 6 meters of glazing right in front of you and you're sitting next to it waiting for your plane? So we started to investigate radiant heating systems. We did a very, very detailed study of radiant heating to determine whether we could make it work or not. And what we determined was that as long as you can put a radiant flooring system that can produce a reasonably high output, say 35 watts per square foot, next to the curtain wall in a band about 10 feet back from the curtain wall, you can generate enough heat in the floor to keep the space adjacent to the window warm. And then you can do other stuff higher up on the window if you need to. So what we did was we got rid of all the radiation elements at the base of the windows throughout the entire terminal building and the public spaces, put in the radiant floors in the floor, and then put traditional radiation up higher in the windows to deal with the windows that are above the occupied zone or 10 feet or so higher. Then the architects went through a further challenge on us. They said, we're not going to put tile in the whole room. We're going to put this nice carpet. We're going to put a really nice thick, 1-inch thick carpet. And we're going to put backing under that carpet because we want to be nice and squishy when you walk down the hold room. So they put basically an R10 insulation value on top of that floor slab, which we're trying to push heat out of. So now you've got a radiant floor that's hot, you're trying to get heat to radiate out of it, that would have to go through a carpet, and only then get to the occupied space and start to do what it had to do. So that was a further challenge. We did work through it. We did manage to work out the right balance of energy versus insulation to get it to actually work, and it does work quite effectively. Now, the reason why the radiant system works so well is, I'm just going to talk a little bit about the heat transfer theory, is there's 3 different modes of heat transfer that you can use in a facility. There's direct transmission, where you have a hot element, you can touch it and feel it's hot, that's transmission. There's convection, where you use a heated element and you move air around it. So an example would be the old style steam radiators you might see in some old houses. It's a hot element that is so hot that it draws air towards it and causes the air in the room to move around. And the final way to transfer heat energy is through radiation, which is infrared energy from a hot source radiating infrared energy across the space and then impacting a surface such as yourself, your skin, your face, that makes you feel warm. But there's actually no heat between you and the source itself. So by using radiation, the radiating floors, we're able to make people feel very, very comfortable with a very low amount of input energy. You don't have to make things very, very hot to make infrared energy work. So the floors at a relatively low temperature, it could be as low as 90, 80 degrees Fahrenheit if necessary, and as high as 140, that's the absolute maximum. But you do get that transmission of energy across through space, and people will still stand there or sit there and feel warm without having to put a huge amount of energy into the system. So the radiant floor is worked out as a highly effective means of achieving sustainability in the building. I'll talk a little bit about the actual real-life results of what we're seeing once they're up and running. One of the things we started to explore, we have this piping system in the floor, and we can pump hot water through. Could we use it to pump cold water through and cool the building using a radiant floor? So we did, again, some analysis on that. It was technically feasible. There's a way to do it so you don't cause condensation to happen on the carpets or the floors where it's exposed, just tile. And we implemented that process as well, too. So we can not only heat the building with the radiant floor in the wintertime, we can also cool it in the summertime using the radiant floor. And that actually had some incredibly remarkable results in terms of performance, which I'll talk about momentarily. This is just some of the lighting systems that we've used in the facility, too. A lot of the lighting is indirect lighting, as you see here, with the light source reflecting off the ceiling as opposed to being shot directly down below. What that does is it allows you to use a high power, high efficiency lighting fixture or lighting bulb or element to project a large amount of light over a large surface and diffuse it. So it's not glaring, it's not very powerful, it's not very disturbing to the eye. It's powerful, but it's allowing for a much more efficient use of the light, and your eyes actually see the light better in this approach by reflecting it off the ceiling. So there are spotlights and stuff in certain areas to highlight certain things in the building, certain elements the architects wanted to highlight. But you'll see the majority of the space uses indirect lighting. And as a result, it's very subdued, very peaceful in there at night. It's not bright and glaring. This is another shot of the curtain wall system, and again, the indirect lights over here. We also used LED elements to, again, highlight certain features. The big field of skylights, or the constellation as it was called by the architects, the skylights. And that's a theme that you'll see throughout the building. This is the first usage of, I think it's the first use of LEDs in Manitoba, of this style of LED. The original concept was to have a white LED, but they were not technically viable at the time. So the blue ended up being the fallback position. It actually happened to match up with the Winnipeg Airport Authority's corporate colors, so it worked out nicely in the end for them. And they're actually quite striking when they're on at night. And it's intermixed with standard, compact fluorescent pot lights and so on and so on. So that the lighting technology through the building, again, is very much state of the art. The opening shot that you saw of the building at night, the illumination of that is mostly strip light LEDs shining up on the overhangs of the facade of the building. So just talking about ventilation schemes in terms of sustainable elements that we maintain in the facility. There's a lot of large open spaces such as this one where you pick up your bags in the hall. They're large voluminous spaces. They're 3 stories tall, thousands and thousands of square feet in area. But all the activity happens down just at the floor where people walk around. Nothing's happening up here. There's no people up here. There's nothing going on up in that space. So one of the design concepts we explored was there a way to ventilate, heat and cool the space without having to ventilate and heat and cool the entire volume of the space. We ended up working with what's called the displacement ventilation system. What it does is it brings high volumes of air at low velocity into the space, and that causes the air, at lower temperature as well too, and that causes the air to stay close to the ground. It doesn't tend to rise as heated air typically would do. So we're not shooting air down anywhere from the ceiling trying to heat or cool out the floor. If you look carefully in these baggage carousels, or when you're there in person, there's a series of openings in the top of them here. They're custom-made grills, the front and back. And basically we're pushing out cooler air at very low velocity but high volume from these openings in the top of the baggage carousels, spilling that air down along the floor and basically treating the lower 10 feet of the total volume of the space and not doing anything with the air up high. Additionally, if you look really, really carefully, this is pretty subtle, there are slots cut into the top of the skylights that allow that air at the ceiling to be drawn back to an air handler and treated, cooled or heated based on what time of year it is. And so that additionally assists this air staying down low to the floor, and any motion of air trying to move it upwards up towards the ceiling is limited. The other scheme we used for the large space was a different aspect. The best way to explain this is if you ever notice when you're in your shower, if you have a shower curtain in your house, or if you had an experience with a shower curtain, when you turn the shower on, the curtain suddenly wants to go into the shower. And that's because the spray of water that's coming out of the water jet is inducing a mass flow. It's inducing a flow of air entrained into that jet as it's coming out of the shower head, and that's why you get that air movement happening. So we use that same effect in the departures hall. You'll notice there's a bunch of what we call eyeball diffusers along here, this strip along here, that are a series of jet diffusers. Basically, they push out air at high velocity, up high, towards the occupied space of the departure hall. You'll notice that each one is sort of at a different angle. It's because they're patterned to shoot close, medium, and then far to try to get the air to move properly in the space. What that does is, for a relatively small amount of fan energy, we push a stream of air about 150 feet out, and it causes all sorts of motion in the space in terms of air getting entrained to that jet. So the overall effect is that there's excellent air movement in the departures hall with very little input from the fan to make that all work. And it's also been commented that the air quality in there is exceptionally high because of that good mixing of fresh air as being pushed into the space. There's no pockets of dead air that anyone's observed. So those are some of the sustainable features, sustainable elements we incorporated into the design. And it's all great talking about it in theory, but how is it actually working? So we can comment about that. We had some 33,000 design meetings over the course of this project. 33,000, believe it or not. This is one of the first one with the major players at the table. This is Fred Clark from Caesar Pelly's office, Mark Shoemaker, Stanis Smith from Stantec Architecture in Vancouver, and a number of the other players on the team. So it was quite an involved process. We had, at one point, probably about 50 people involved in the design work. And that was, of course, over 3 or 4 years, and then another 50 or so involved in the construction aspect as well, too. So it was quite a substantial project. So how's the building actually performing? I'd have to say it's performing very, very well, in our opinion. There's still a lot of ongoing commissioning work happening, so we don't have a lot of hard information in terms of BTUs per hour or kilowatts that we can speak to. But from observation of the commissioning process, which has been going on for about 2 years now, the building's been open for just a year and a half or so, we're seeing excellent performance through basically 2 seasons of full operations, winter, summer, fall, that kind of thing. The biggest thing that I'd comment on is the radiant floor system. We expected it to work very, very well. We didn't expect it to work as well as it actually is performing. It's quite impressive. Basically, when the building first opened, the radiant systems weren't functioning because of some control issues that were being ironed out. So we were having to heat the building with all air in most spaces. When it started to get colder, we saw the air systems being able fully to do that, not a problem at all, but we saw the boiler plant being loaded up at the central utilities plant. A lot of energy was being required to make this all work. As soon as we turned the radiant floor systems on, we started to overheat the building significantly. We cut back on the air, and the radiant floors would start to perform very, very well. We found that we actually had to dial the radiant floors down quite a bit in order to make it comfortable for people to stand in spaces, because it was just such an intense amount of heat that these very, very large areas of floor were producing. The worst case was in the passenger security clearance area, where people are waiting in line to go through the security gates. And you could be waiting 10, 15, 20 minutes, depending how long the lineups are there. And we found that particular area, because of the ceiling height being so low and the radiant floor being right there, fully exposed on tile, it made the place actually uncomfortable, so we had to turn that floor down quite a bit. That we did not expect to have happen. So again, it speaks to the efficiency of the systems that were installed and how well they worked, and exceeding our expectations. What we found in some areas is that the radiant floors actually serve as the primary means of heat, that we actually can set a baseline of heating for the building using the radiant floor, setting it at a particular temperature, just leaving it there, and then trimming the temperature of the space by adjusting the air temperature on the air handlers. And what that ends up doing is it's saving a huge amount of energy from the central utilities plant, because we're using a very, very efficient way to get temperature into the space with low intensity heat, so we don't need a lot of energy to do that. And we also reduce the amount of effort the fans and fan systems have to put into heating the air in the building itself. So that's worked out very, very well in terms of the efficiency side. What's even more remarkable is on the cooling side. When we put the radiant floors on this past summer and really gave them a good solid test, we found that basically we could cool the entire building with the radiant floors alone. We didn't need to do any air treatment apart from whatever fresh air is coming into the building and being treated from outside air conditions. The chilled water system coupled with the radiant floors is in fact so powerful that you can very much overcool the spaces. We actually had one area where it got down to about 10 degrees Celsius one night just on air conditioning, and it was 35 degrees Celsius outside. So it was basically a meat locker. So what we found is that we had to go back and reprogram all the controls to get a better balance of heating and cooling and air temperature to try to make sure that we're not freezing passengers in the morning after the building's been cooling off overnight in the summertime. And that's worked out very, very well as well. What we found was by the end of the summer, the central utilities plant was able to shut off one chiller altogether. Where we were, say, running 3 chillers, we were running the building on 2 chillers as a result of getting those systems commissioned properly. So they have lots of available cooling, and the building is making use of that very, very effectively. I'll just touch base quickly. I think we're getting close on time. One other system that I won't get into great detail about, but we do also use a condenser water loop inside the building that recycles heat within the building. So any area where there's, say, a computer room, a store that needs air conditioning all year round, a restaurant, that kind of thing, we have water-to-air heat pumps in those spaces. So we extract whatever energy is in that space, whatever heat they don't need, compress it and put it onto a condenser water loop. So basically there's a loop of water that just pumps water around the building. We inject energy into that loop, and then other devices in the building where they say might need heat are able to extract that energy and reuse it somewhere else. So it's basically an ability to move heat from one spot in the building to another spot using this loop. So what that allows the building to do is to self-heat and self-cool if necessary. So for example, if you have a data center, we've got a large rack of computers making heat. That heat can be extracted from that space, put onto this energy bus, and then moved over to a space where, say, you might need heating for another reason. It's cold in that space. So we effectively move around approximately 1,500 tons of cooling within the building across this loop. What we do also have on the outside, if there's an excess of energy in the building, say in the summertime, we have 8 very, very large food coolers out here to dissipate that energy to the outside. So that's why you're seeing these substantial pieces of equipment when you drive up and look out the window. So I guess in a nutshell, the question was posed, has sustainable design enhanced the performance of the building? And I would say yes, that definitely is the case here. The process of the sustainable design approach assisted us in coming up with unique solutions to some problems we were presented here in terms of the architecture. It allowed us to design systems that have proven more than effective in terms of their expectation. And I think it's allowed us as a team to provide the airport authority with a facility that is, as they say, iconic, not only from its architecture, but also from its performance. And we're hoping once the commissioning process is completed, we can start to document that and present further positive results as a result of that. Thank you.
For the questions, can you repeat the question?
Yeah.
So we have time for questions. So we encourage you to ask some questions now for Russell.
Yes.
I assume you set an energy target for the facility, and your target is probably related to the national energy code for buildings. So, did you use the ECB as benchmark, and if so, what was your goal energy
Okay.
for the code?
Yes. Do you want me to repeat just for the microphone? Is that the purpose? Okay. So the question is, what was the energy target we set for the building, and did we use the National Energy Code as the part of the scheme? The answer is yes, there was a target set. I don't remember the number off the top of my head because it was a long time ago. But we did follow the National Energy Code scheme. We went through the CBIP process at the start to do all that modeling, and we ended up being 50% above the National Energy Code for a building of this size. So, yes, sir.
How much would you credit the ability to run the building as due to the fact that it's extremely airtight building?
I think the building envelope definitely assists the whole issue that we have about pressure, the pressure equalization on the north facade of the building. That remains an ongoing concern in terms of getting the facility properly commissioned for pressure control. We've just got so much square footage of glass there that any little wind starts to play havoc with systems on the opposite side of the building. So what we've had to do is implement some different control schemes to try to dampen that effect. And I think the quality of the curtain wall definitely assists in reducing much more major concerns that could have happened.
What would you have had to do to go for the next level of leads? Was that in geothermal heating or something?
Geothermal would have played a part. In fact, it actually did play. We were just talking about this before the presentation. Geothermal was on the table up until probably 2 years before the construction started. We actually went and designed a geothermal system for the building, had it costed, had a proposal put to the airport authority to consider it for the building. Would have done about half the energy plant for the facility, but they opted not to go with that option for a number of reasons that I can't talk about. But it was on the table, and that definitely would have pushed us up to the next level, yes.
The reclaiming of heat, do you normally see that in other buildings like data centers and where there's lots of waste heat generated for industrial environments?
It really depends on the application. Heat recovery is fairly common in Manitoba, just given where we live. The sort of heat recovery, we are doing traditional heat recovery in this building as well, which I didn't talk about, but the recovery that we're doing, say, out of the computer data centers and stuff, that's a bit unique. But it is becoming more and more popular now as people are starting to look at sustainable designs for buildings. Yes.
Whether the project was conventional or geothermal, it seems that controls play a very important part.
Yes.
In the design. Did you estimate or underestimate how much fine tuning it would take in the building to get the comfort that you expected, or pleasantly surprised?
The question is whether the controls are critical to the building. The answer is yes. The control system in this building is very, very sophisticated. It's probably one of the most sophisticated ones I've worked on. The expectation for the fine tuning, I think, was there to a certain extent. But when you get into this caliber of building, you're sort of doing some experimenting as you're designing, because you're being asked to do something that no other building does, right? So you have an expectation that there will be some fine-tuning work, but what we've seen here is some systems work perfectly well the first time. Other ones we had to go back and say, this isn't working as well as it could. How can we adjust the design of the controls to make it work? And that has occurred in a couple instances. Say the pressure control of the building is one of them, for example. But they are definitely critical.
Do you find that you have a lot of redundancy in the design?
The nature of this building's design is that there's inherent redundancy. So, like I mentioned before, we can heat the building without the radiant floors. That's not a concern. We don't want to do it that way, but we can't heat it no matter what. There's always, because it's the type of building it is. It's an airport. It has to be fairly bulletproof, right? So there is redundancy, yes. Sir.
Are you using a post-occupancy evaluation to fine-tune the control and operation of systems in the building?
Sorry, I missed the first part.
Are you using a post-occupancy evaluation, sort of asking people working in the building, their satisfaction with thermal comfort and work quality, lighting, and so on, using that feedback to fine-tune your sort of commissioning of the...
We are doing it, but not in a formal process. It's more the airport authority is very, very, very attuned to their tenants, their clients, and their customers. So they monitor, say, Twitter feeds and that kind of stuff. And if someone's saying, hey, it's hot in the airport, that gets up the food chain to us and say, why is it hot over here, guys, kind of thing. So it's an informal process, but yes, they are doing that. And there are things like issues with glare, for example, they're dealing with through that process, and other things like that. Yes, sir.
How many person years were put into the design part of the building?
Whatever 4 times 50 people is. So 200, yes, right. So it was a big effort, yeah.
Is there a SEER value you could put on the design of that building, or has it been met or attained?
It's very, very difficult to do that with this type of modular plant. I guess we could work it out. I don't know what it would be off the top of my head, no, unfortunately. There's more than just the chiller plant I talked about. There's other subsidiary plants. There's other refrigeration systems in there that all form part of the network of the cooling for the building.
What about tonnage?
Well, the campus is 2,500 tons, plus 300 in the building itself. So there's, I'd say, around 1,750 for the building itself. Do you have any questions from the internet at all? Or? No? Okay.
Is that all the questions, or?
You speak of heat recovery. Have you considered the engines that run every day?
From the aircraft, you mean? We thought about it. I don't know how you do it. It's very, very difficult to... Okay, well, if you have a scheme, I'd be interested in knowing how to do it. Okay, good.
They're going to put them in touch with you.
Yeah.
So it's a lot of BTUs there.
Oh, yeah, a lot of air, too.
Spoken of our appreciation.
Oh,
Russell.
okay.
Thank you for speaking.
Thank you. Thank you. Okay.
So, Tommy also mentioned something really quickly too here. We just got some breaking news here. Mike Millardy with Southern Comfort Mechanical. We're doing a joint project on the Cornerstone Housing Corporation. And Mike, he went for an Excellence Award with Canadian Geothermal Alliance. And they have won. And that was part and parcel to our partnership with monitoring. So, congratulate Mike.